All right, good morning, everyone. Can you all hear me okay? Hoping so. I'm going to share my screen. Oops. Perfect, thank you so much. Share. Is the screen good to go? You can all see Mathematica? Let me just type. All right, wonderful, wonderful. So we're going to begin. How is everybody? You all doing good? Hoping so. Hoping everyone's doing good. Today is very special because today is the last, I don't know how to say this, tested lecture, if you will. We're going to be doing an example of the Rayleigh-Ritz method. And then after today, the only thing left to really talk about is the finite element method. Now, of course, finite element analysis is not simple. It can become very complex. And it's hard to actually teach because the applications of it are extensive. It's used in chemical engineering, geotechnical, structural, mechanical, you name it. They all use finite element method. So that's why it's hard to teach. I remember when I taught it in winter semester, it is Civi 665. I had a lot of chemical engineers asking me about chemical processes. I had no idea. I had a lot of mechanical engineers asking about dynamic simulations, which I knew a little bit of, but it becomes challenging because the topics are so broad when it comes to the finite element analysis. So what I'm going to do for this particular course for the finite element analysis portion is I'm going to spend Tuesday next week basically just going over the basic theory, very, very basic theory. And then after that, we are going to use Abacus to just kind of play around and solve some examples that we normally couldn't do using our traditional theories. So that's the plan, at least. We'll see how well that goes. But again, today is special because it's the last real tested lecture day. I just want to say thank you all for the wonderful semester. It's been absolutely fantastic being with you guys through the return to in-person classes. It's been great. You have all been super nice to me, which is weird. I hear third and fourth years are usually pretty mean. But no, you guys were all awesome. It was absolutely fantastic, so thank you all for that. I'm also happy to report that the students came in clutch with the USRIs, and we are over 75%, so I will be doing the second review session. It's funny because USRIs were supposed to close last night, which is why I sent the message as kind of a last minute thing. But now I notice that they've been extended for 2 more days. So I kind of look like a weenie sending the message to everybody, but oh well, it is what it is. All the requirements have been met, so we'll have a lot of final exam reviews. Referring to the final exam, it's not going to be as difficult as the midterms, at least that's what I'm trying to accomplish with that. So there hopefully shouldn't be too much to worry about. My goal for the final exam, because I've gotten a couple questions, would be this. The final exam is cumulative, basically meaning it's going to cover everything we've done in this course. Now, if you look at midterm 1, there is an exam review. If you look at midterm 2, there are 2 exam reviews. And for the final exam, there is 2 final exam reviews. Basically, what I want from this course is that if you were to just watch and learn from the 5 exam reviews that will be posted, that should be all you need to basically obtain a good mark in the final. I don't want the final to be stressful. It's right before the holidays. I know that everyone's tired, beat up from the semester, and all basically everyone wants to do is just relax. And that goes for me too. I want to just relax. So if you were to go through the final exam and the midterm exam reviews and you say, you know what, Clayton, this is pretty good, you should be in a very good position for the final. Now, the final is on eClass. I'm actually just going to pull eClass up on screen here, so I'm hoping that you guys can see it. If we look down under assignments, final exam at the very bottom tab, it has the date December 16th. It is from 2 to 5 o'clock p.m. Mountain Standard Time, so it's going to be 3 hours, and it's going to be 50 multiple choice questions. Now, I also have a question breakdown right here because I know a lot of students are going to ask. And basically, it's going to be 5 questions from topics 1 and 2. That's basically the linear algebra review. It's going to be 15 topics, or 15 questions from topics 3 to 6. So that's basically stresses and strains. And then it's going to be 30 questions from topics 7 to 10. So those are basically our approximation functions. Euler-Bernoulli beams, principle of virtual work, Rayleigh-Ritz method, etc. So it shouldn't be too bad overall. And it's one of those things that if you want to try and guess how you're going to do in the final, basically what I am anticipating, we'll see how this goes, is whatever you have as an average for your 2 midterm marks, I want your final mark to be at least 20% higher, or if you already got 100%, I know there's a couple of you trolls out there, basically just another 100%. And I want to achieve this by again, the final itself should be easier than the 2 midterm exams, and B, I'm going to award partial marks. So again, the final exam is actually going to be kind of a PDF document I send out. You can print it, you can put it on your tablet, or you can just have it on your computer and write on loosely for engineering paper. And basically you are going to submit a file. It's going to just contain your answers to your questions along with any work. And if you have work and your answer is incorrect, well then I'm able to award partial marks. Again, that's all I want basically from having it written in a way, is that it gives me the opportunity to award partial marks. You will not be penalized if you do not show work. So let's say it's a very simple question. You're thinking, you know what, this is trivial, I know the answer. Well, then you can just circle the answer. If you just provide an answer and it's correct, well then you're still going to get 100% on the question. I'm not going to take away any marks. Again, this is just an opportunity for me to award extra marks for you guys. That's all I want. I want, again, this to be nice and easy. I heard rumors that on the 15th, now this could be completely incorrect, I'm not sure, that is when the 372 Dr. Yong's final is. Is that true? Is it on the 15th? I'm just going to shut the window really quick. Oh, 13th. Interesting. I was thinking to myself, the best thing that could ever happen would be kind of a collaboration on exams. You know how in some exam questions you have to use the previous question to answer the next question, etc.? Imagine if I were to combine and collaborate with Dr. Yong for that. Basically have a displacement question from his course, and then for this course you calculate strain or something like that. Oh, wouldn't that just be awful? And then incorporate 374 right after. Or if you know the stresses, can you design it? Well, that would be a lot of fun. I guarantee that all of you would absolutely hate me, so it definitely will never happen, but I don't know, just a fun thought that came across my mind. Yeah, exactly. Don't worry. I wouldn't do anything like that. Alright, so that's basically it for what I wanted to talk about this morning. Again, just a reminder, assignment 11, if you haven't submitted something, basically just watch a movie, watch an Oilers game, have fun, relax, and just let me know that you've taken the time to relax. I want to give everyone 100%. Again, it doesn't even take a lot of effort. I've gotten messages that said, Clayton, I watched a movie. Perfect, 100%. I appreciate all the students that gave me those nice long responses. It's not only nice to know that you're relaxing, but it's also nicer to know you all as a person. That's kind of the hard part about still having some students online, is that I don't really get to know you like I normally would. So it's been a lot of fun in that regard. All the grades are in the grade book. It's in an actual Excel sheet. It's not. Let's see if I can even pull it up without. Actually, I can't go to my email. I'd violate a lot of privacy. It's in a separate grade sheet, so it's not on eClass yet. So if it says that you're 0 for assignment 11, again, don't panic. It's just because it's in the grade book. Once all the grades are submitted for the assignments, I'm going to basically update everything and then give you all the chance to kind of say, hey, you know what, Clayton, on this assignment, I think my mark should have been this or whatever. So you don't have to worry too much. There will be an opportunity to basically verify everything, which is what I want. I don't want you to feel that there's some secret stuff going on in the background, because there's not. I'm not that creative. All right, so is there any questions from you all before we begin today's example? Or is everything pretty good? I'm hoping pretty good. It looks pretty gross outside. I picked the best days to have online lectures. All right, I'm not seeing anything in chat. If you have any questions, again, throw it out in the chat. I'm going to move on to the question now. But again, if you have any questions, just throw it in chat. I'm happy to answer. So as promised, our actual example today is going to be the assignment question. All right, we're going to do it together. And I'm going to post the code after class. So if you want, you can just use the code. By the end of today, you should basically have assignment 10 completed. No problem at all. The only thing I'm not going to do is this last part, which says comments on the accuracy of the approximations. By the end of this, though, it'll be pretty clear what exactly is happening. So I just picked a random preview. We have some variables here. And the first thing that we are going to do together is basically code this program, whatever you want to call it. So if we look at our beam down below, it's a very unique beam where it's fixed on both ends. And the only load acting on our beam is going to be that point load P, which acts at a distance D from the left-hand support. Now, if we were to look at the question, it wants a couple things. First is the exact displacement, both in this first region from 0 to D, and then in the second region from D all the way to L. Then it wants the strain energy stored in the beam, and then finally the approximate displacement solution using the Rayleigh-Ritz method for a second, fourth, and sixth degree polynomial. As we're going to see, the process is going to be extremely similar to virtual work, but it's actually easier than virtual work, as at least in my opinion, but I think that you all will kind of agree to me, or with me. So what we're going to do is we're going to jump into Mathematica. And the first thing that I like to do in Mathematica is have a function to basically clear all of the variables. The biggest problem that I've seen thus far in Mathematica is that the dsol function won't work for a lot of students. They all say, you know what, Clayton, the dsol function is just not working. It's giving me an error. The key to the dsol function is every time you use it, basically your equation that you want to solve for, in this case it would be our displacement or something like that, it has to be unknown. Again, the whole purpose of the dsol function is to solve a differential equation. If I were to run my program the first time, basically it solves that differential equation and it stores it. So if I were to not modify my code and run it a second time, the dsol function will report an error because you're trying to solve for a function that in Mathematica's eyes is already known. That's the problem that happens. So to do this, I just go clear global star that. A little reminder that this key right here, this is actually the same key as tilde. It's just to the left of the 1 key. It's not next to the enter key. And the reason why I prefer this rather than clear all is because if you were to use clear all, or if I were to simply go, let's just say clear y, there will be some problems later on when we get to the actual dsol function. So clear global is a great way to ensure that everything is being cleared every run. So that's the first thing I do. It's the same as MATLAB. Usually your first MATLAB lines are clear, semicolon, CLC, something like that. This is basically taking care of the same thing. The next thing that I personally do in all my codes is I want to list all my parameters. So I'm just going to make a parameters section as follows. And basically we are just going to copy all the parameters that we were given. So if we were to look here, we are given quite a bit actually. The first one is that the beam below is subjected to a point load P of 12 kilonewtons. So I'm going to come down here and say, you know what, okay, perfect. We have P and it's equal to 12 kilonewtons. Now, there's a couple things that I'm going to ask you guys, the chat. The first one is this defined correctly? Did I do a good job defining P? Or should I modify it in any way? What do you think? All right, you guys are on your game? Negative. And the reason why, as we can see in our diagram, P is going downwards. So we're going to have a negative. The second thing I'm going to ask you is, do we want it as 12, which is basically kilonewtons, or do we want it as 12,000, which is newtons? What do you think? All right, I see 2 votes for newtons. Anyone voting to keep it in kilonewtons? Oh, so we got some discrepancy here. Yeah, let's see, one more answer. Okay, so Matthew kind of hinted to what exactly I was going to get at. What I like to do is I like to keep everything in terms of MPa and newtons. But remember, if I were to do that, it means all of my answers are in terms of millimeters, which is normally fine because in structural engineering, our beams usually deflect in terms of millimeters. If you were to have a beam deflect in terms of meters, you got big problems on your hands. But if we were to look at the assignment, and this is kind of my hint, it says right in the assignment that it wants everything in terms of meters. All right, meters. So if that's the case, I don't want to use newtons, MPa, and millimeters. I actually want to use kilonewtons, kPa, and meters. That way all three always work with each other. So in this case, having 12 as kilonewtons, I'm actually just going to leave it as that. And since I'm wanting everything in meters, one thing to keep in mind is that all my distances must be in meters, and all of my stresses, basically the Young's modulus, has to be in kPa. So that's why I'm going to keep it as such. If you wanted to, you could have everything in newtons, MPa, and later millimeters. You're just going to have to convert it accordingly. So I find it's best to just keep it all in kilonewtons, kPa, and meters, and then I don't have to worry about the conversion later on. So I'm just going to leave it as 12. The second thing that we have is the point load acts at a distance d, which is 3 over 2 meters from the support. So I'm going to go d is equal to 3 over 2. Now this is something that's going to play a role later, so I'm not going to show you why just yet, but one thing that you'll notice with me a lot of the time in Mathematica is if I were to have a fraction, I'm going to keep it as a fraction. I don't want to put it as 1.5. I'd rather keep it as a fraction. Again, it's not going to be very clear right away why I'm doing this, but later on you'll see, okay, that makes sense. So there's the first two. Later on in the question it says that the length L, Young's modulus E, and moment of inertia I are 10 meters, 20 GPa, and 3 over 1,000 meters to the fourth respectively. So I'm just going to come in with those. We know that the length L, 10 meters. It's already in meters, we're good to go. The Young's modulus, which I'll put as EM. Again, the reason why I'm putting it as EM is if I were to take away the M, the variable turns black, meaning it's already defined. So I actually can't store any variables that are already defined. I have to make it blue somehow. So if I were to put an M there, as we can see, it now turns blue. It's undefined, we're good to go. And we said that if we want meters and kilonewtons, then all of our stress units have to be in terms of kPa. So I'm going to say, okay, well, we have 20 GPa, and if I were to add 3 zeros, 1, 2, 3, we now have MPa, and if I were to add 3 more zeros, 1, 2, 3, we now have kPa. So that's what I'm going for. So that's good to go. And then the last thing was the moment of inertia I. Again, if I were to put I by itself, as we can see, it's black, it's already defined, so I have to pick a different variable. In this case, I just go IG, or basically the gross moment of inertia. And we are given that as 3 over 1,000. So I'm going to go 3 divided by 1,000. The units are already in terms of meters, so we are good to go. So that will be all of my parameters for the question. Is there any question concerning these parameters, or is everyone pretty okay with the parameters section? It's basically just inputting what you have on the screen. I'm assuming that everything is good. Again, if you have any questions, just let me know. The only thing that I want you guys to kind of keep in mind as we go through, because I'm going to minimize this screen right here, is that we have a fixed end beam. Okay, so both ends, the left and the right, are fixed. So that's going to be one of the things to remember. Another thing that I'm going to define really quick, just for completeness, I think would be the best word, is what is our distributed load acting on this beam? What do you guys think in the chat? What would my Q be equal to? If I were to define Q, our distributed load, what would I put it as? 0, exactly. There's no distributed load. The reason why I'm adding this is because I don't want to create a code that just works for one scenario. If I were to give you the same question with the distributed load, I want your code to be able to basically handle that without a problem. So I'm going to account for Q, even though in this particular case we do not have Q. The last thing we're going to talk about really quick before I minimize this side is this. If I want the exact solution of this beam right here, can I solve it using just one differential equation? What do you think? Can I solve the exact solution of this beam with just a single differential equation? No. Yes, exactly. We actually need two. And the reason why is because this point load P right here creates a discontinuity in our shear force diagram. And basically, if we have a discontinuity, we actually have to have separate functions defining both the left-hand side as well as the right-hand side. So basically, we need a differential equation for this side right here from 0 to d, and we need a differential equation for the other side from d all the way to L. Now, one common misconception is this. I would have to use the d-solve function twice. When we're solving two differential equations, we actually only use the d-solve function once, because as we can see, at point D right here, we're going to have a lot of boundary conditions that relate the left-hand displacement to the right-hand displacement. So since our two displacements are two separate functions, but actually they're intertwined with each other, we have to use the d-solve function basically just once. So you all have this picture of the beam. I'm going to minimize that. Oh, no, minimize that. I'm going to pull up Mathematica, and we are going to start solving for the exact solution. So this would be the first part of the question, exact solution. Now, the first thing I'm going to do for simplicity, because as we know for Euler-Bernoulli beams, a lot of them rely on an EI term, which is basically a stiffness term. I'm just going to define EI as EI. So I'm going to have EI is equal to EM times IG. Again, this just makes it more simple so that instead of having to type this out many times, I only actually have to write out this right here. So that's going to be the first step. The second step I'm going to do is I'm going to define my differential equation for both the left-hand side of the beam as well as the right-hand side of the beam. So I'm going to say my differential equation for the left-hand side of the beam is going to be equal to EI times the fourth derivative of the displacement function. In this case, I'm going to call my displacement function YL, because remember, we're going to have two different functions based on which side of the beam we're looking at. So for the left-hand side of the beam, I'm going to call it YL, or basically my displacement function for the left. And this is to basically the fourth derivative, so I'm going to go 1, 2, 3, 4 derivatives, and we know it's a function of x1. Now we know that technically this term right here in our differential equation is equal to our distributed load Q. So what I'm going to do is I'm going to move the distributed load term to the other side to basically get minus Q. Now we know that since I moved Q to the other side, this whole term right here has to equal 0. Again, Q doesn't matter in this problem because, as we can see, Q is equal to 0. But it's one of those nice things that if I were to give you the same question maybe on the final and it had Q, all you would have to do is literally add, I don't know, 10, and then the code will still work the exact same. Isn't that nice? That's the nice thing about code, is it's easily modifiable to any situation you can imagine. So this would be my differential equation for the left-hand side. But we said that we also have a differential equation for the right-hand side. So what I'm going to do is I'm going to copy it because it's going to have the same form, and I'm just going to paste it down below. And instead of differential equation for the left, well, this will be my differential equation for the right. EI, well, that's going to be the same, but here's the nice thing, and I'll ask you guys this in chat. You know that from 372 that you've taken with Dr. Yang, that he loves scenarios where on one side of the beam it's, let's say, 2 EI, and on the other side it is just EI. If our beam, I'll pull it up here, if our beam, we were to say that the stiffness on this side of the beam was 2 EI, and the stiffness over here was just EI, could we account for that by just simply going, just 2? Could I do that and basically still obtain the exact solution? can I account for the different stiffnesses throughout the beam? What do you think? Yes. And the answer is yes. Isn't that extremely beautiful? Which is great because sometimes you'll never see a beam that's basically 2EI versus EI. But one of the things that you might see is, let's say that this part right here was made of concrete and this part right here is made of steel. We know that the stiffness of steel and concrete are going to be different from each other. So in cases like that, it would be useful to know how stiffness basically works. But back to this equation, so EI stays the same. Displacement function for the left, well, we know in this case we want a displacement function for the right. So that's all the modifications. Q is just going to be the same. So we've now defined our two differential equations. From here, it's nice and simple because once we have everything defined, we can go right into solving these two equations. So I'm going to go sol, or my solution, is equal to, and I'm going to use my dsolve function. We've already talked about it quite a bit. So dsolve, it's basically just the solve function, but the d right here basically means differential. So it's solving a differential equation rather than a linear or nonlinear equation. And inside of the dsolve function, we need three different arguments. So I'm going to separate those with 2 commas. Argument 1 here is what are our equations and what are our boundary conditions. Argument 2 is going to be what equations do we want to solve for. And then argument 3 is what is the variable in these equations. So I usually work from right to left in this case because it's easier to fill out the right-hand side than the left-hand side. Again, the very right-hand component, or the third component, is simply what is the variable in these equations. And if we were to look up, well, our functions are just a function of x1. That's the big thing. They're just a function of x1. So our variable is going to be x1. The second one over here, again, is what equations are we trying to solve for? Well, we know that we want to solve for the displacement function for the left-hand side, as well as the displacement function for the right-hand side. So what we would do here, if we're ever inputting multiple arguments into Mathematica, we need squiggle brackets. Again, squiggle brackets just means that we can input multiple things. So we're saying, okay, the first one I want to solve for is my displacement function for the left-hand side of the beam, which is a function of x1. And then the second one is going to be my displacement function for the right-hand side of the beam, which is a function of x1 as well. So that would be this part. Again, we are only going to use one dsolve function to solve for both of these displacement functions. We're not going to use it twice. We're just going to use it once. Now the first part, which is going to suck the most because we have so many, is what are our equations and what are our boundary conditions. So the first easy one is we have our two differential equations defined above, right here and right here. So we know that our differential equation on the left-hand side has to be equal to 0 because we already moved q to the other side. And we know that our differential equation on the right also has to be equal to 0. So the key thing here, double equal sign. That's going to be important. So now the question becomes, okay, I have my two differential equations defined. How about my boundary conditions? So the boundary conditions are usually what's going to suck the most. We've already covered in depth that if we had one Euler-Bernoulli differential equation, we needed 4 boundary conditions. But if I'm trying to solve 2 Euler-Bernoulli differential equations, how many boundary conditions am I going to need? What do you guys think? Aaron, I think you were anticipating that question because you were pretty quick on the trigger. But yes, the correct answer is 8. Basically, we need 4 boundary conditions for both of these equations so that in total we would have 8. Now, if we looked at our beam, it's pretty simple that both ends were fixed. So I'm going to start with the simple ones, which is fixity on both ends. So we know on the left-hand side of the beam, which is governed by YL, we know that the displacement and rotation at 0 must be 0. So YL at 0 is equal to 0. YL prime at 0, which is the rotation, is also equal to 0. And if we look at the very right-hand side of the beam, we know that the displacement and rotation at x1 is equal to L also has to be 0. So y on the right-hand side of the beam at L equal to 0, yr at L equal to 0, and this is actually yr prime. So basically the displacement and rotation at the left-hand side is equal to 0, and the displacement and rotation at the right-hand side is equal to 0. So there's 4, but we need 4 more. So I'm going to pull up the picture here, and we're just going to take a peek and say, okay, if we wanted to, what would our other boundary conditions be? We've already accounted for everything on the left-hand side. We accounted for everything on the right-hand side. Where are my other boundary conditions going to occur? What do you think? We already took care of x1 is 0. We took care of x1 is equal to L. Yes, perfect. So Quinn answered it. x1 is equal to D. We have boundary conditions right here, because we know that if the beam were to displace, there shouldn't be a sudden change in displacement at this point. The beam should be continuous in terms of displacement. So we know that the displacement for this equation at point D must be equal to the displacement of this equation also at point D. Same thing for rotation, and same thing for moment. So what I'm going to do is I'm going to come down here and say, okay, my next one is the idea that my displacement at D for my left-hand side equation has to be equal to my displacement at D for my right-hand side equation. So this is ensuring that the displacement at D is the exact same for both equations. We can repeat this process because we know that the rotation must also be the same. So YL prime at D has to be equal to YR prime at D. And then we also said that moment also has to be the same. So remember that moment is EI times Y double prime at D. And I guess this is YL. And this has to be equal to EI times YR double prime at D. Remember how I said that in some scenarios we could have the stiffness on the left-hand side as, let's say, 2 times something? And this is why we want to include the EI term. I know a lot of you in your code, from what I've seen, just get rid of it because it's equal to on both sides. But just keep in mind later on that there could be a trick where one stiffness is greater than the other, and that's why it's important to actually have these EI terms. I just want to let you know that. So he's saying, okay, we now have 7 boundary conditions. We only need 1 more. And if we were to look at location D, we've already covered displacement, rotation, and moment. And we know that there is actually a 4th internal force for us, which is shear. So what I'm going to do is I'm going to say EI times the 4th derivative of the 3rd derivative of our left displacement function at D is equal to EI times YR, 1, 2, 3, at D. Oops, not capital D. So this is what I did for shear. I basically said that the shear on the left of point D is equal to the shear on the right of point D. Is that correct? What do you think? Is that a correct statement? My shear on the left of D is equal to the shear on the right. No. And the very simplest way of picturing that is we know if we were to draw a shear diagram, we know that there'd be kind of a constant shear here because there's nothing going on. But when we have a point load, we know that there is a sudden drop, either upwards or downwards. In this case, it's going to be downwards. So we know that the shear on both sides is actually going to be different, and the magnitude of the difference is actually going to be equal to P. So let's answer this question because I think this will help the best. Which side, left or right, will the shear be higher? Which side will have a higher shear, the left or the right side? All right, Aaron says left. Anyone want to agree with Aaron? All right, left, you all agree? It is the left side because it starts higher, and at the load P, we have that drop downwards. So what we're going to do is we're going to go back to our code and say, okay, on one of these sides, I'll just keep it highlighted. On one of these sides, we have to add P. And remember above here that we defined p as negative 12. So which side would I add it on, the left or the right side? If I wanted to add a plus p, is it going to go on the left or is it going to go on the right? All right, some discrepancy in chat, left, right. The answer is going to be actually on the left side. We're going to go plus p. And the reason why is this. If we were to look at this equation, we basically said on this side over here that the shear on the right is equal to the shear on the left plus p, but p is negative. So basically the shear on the right is equal to the shear on the left plus a drop. Plus a drop. So there's the key here. So that should be good to go. Any problems with my differential equation? What do you think? Is there any problems with it? Any problems with the differential equation? Who's willing to risk and say, you know what, Clayton, you did a great job. Looks fantastic. We're good to go. Anyone think of that? Beautiful job? Well, honestly, I have no idea. So basically what happens is the best way to figure it out is just to run it. I got a question, no Q. Yeah, in this particular case, we don't have Q in our example. Q is equal to 0. If we wanted to put Q as, let's say, 10, well, it's fine because it's already accounted for in our differential equations, which are accounted for in these two locations here. So we can modify Q if we want to, but we're just going to keep it as 0. But again, if you want to figure out if your code's working, we'll just run it. We ran it, and as we can see, we now have our two displacement functions, and they're just a function of x1, which we want, so we're actually good to go. I always get nervous running code because you never know what's going to happen. The last thing I'm going to do for simplicity is I'm just going to take my functions and store them as variables. So I'm going to suppress this. I'm going to say YL and YR are equal to, sorry about that, had to scratch my head, YR, and they're as a function of x1. When solution at 1. So basically it's saying that YL as a function of x1 and YR as a function of x1 are equal to the solution of 1, which are these two right here. So we're just storing them basically. If I were to run this, we now have them stored. So if I wanted to, I can call YL and I can call YR, and we have our two functions. So we're looking pretty good so far. What I'm going to do is I'm going to start displaying results, because if you look at your question, the first thing it asks for is what is the exact displacement from 0 to D, and what is the exact displacement from D to L. And it gives it in a very particular form. It wants something times x1 squared plus something times x1 cubed. So we want this in this expanded form. So right now, as we can see, it's not really in an expanded form. So I'm going to delete this. I'm going to create a section saying display results, something like that. And I'm going to say the exact solution left side, and I'm going to put YL. And here's the key. If you want it in this form that we have in the assignment, this expanded form, what we do is we go expand. Oops, if I can spell, of course, expand. So if I were to do that, as we can see, we now have it in this form. A good way to check almost immediately in the assignment if you did it right is, as we can see, we have it as x1 squared and x1 cubed. We don't have an x1, we don't have a constant, and we don't have x1 to the 4. If we look at the assignment, we have an x1 squared, we have an x1 cubed, we're good to go. If we were to look at the second part here though, notice that we have a constant, we have something times x1, and then something times x1 squared. So hopefully, when we do the right-hand side, so I'm just going to copy and paste this. If we were to do the right side, we get all those constants and that linear term. And as we can see, we do. So hopefully that makes sense on what to do for the exact solution. How are you feeling so far? Are we good to go? Is the exact solution piece of cake? Everyone happy? Hoping so, at least. All right. If you have any questions, throw it out in chat. So the next part, if we were to just go down the entire question, is it says, what is the strain energy? Strain energy. So the first trick that not trick, I'd say more of a trap, is that students will go to the strain energy section of the notes, they'll find the equation, and then they're going to try and play around with it. But as you're going to see, if you want the total strain energy from that section, you need to integrate over the beam. We need to integrate from 0 to L, negative h over 2 to h over 2, as well as b, right? I'm hoping that you guys remember that. Question for you all, though. Does the assignment give you what the height and the base of the beam are? What do you think? Does it give you the height and the base of the beam? No, exactly. So what actually happens is the first trick is that you don't go to the strain energy lecture. We can go to this lecture, the Rayleigh-Ritz method, because we said that we have an internal strain energy term right here, which is the integral over the domain of u bar. So it's the same formula as before, but in this particular slide, we actually were able to simplify it into this right here, where it's the integral from 0 to L. Oops, I don't want to be highlighting everything. The integral from 0 to L, actually let's zoom in a bit, of EI divided by 2, which we know, multiplied by the second derivative of our displacement function squared. That's all it is. We know EI, we know our displacement function now. There is actually no unknowns in this equation. So what I'm going to do is I say, okay, we found our exact solution. We can actually find our strain energy. I have to put a capital. My OCD would go way too crazy. So I say, okay, my strain energy is equal to an integral. So I'm going to use my integrate function in Mathematica. And the integrate function takes two arguments. The first one is, what is the function you want to integrate? And the second one is going to be, what are your bounds? So we'll start off with the bounds. We know that we want to integrate x1 from 0 all the way until L. So we have no real unknowns here. And the function we want to integrate came directly from the notes. We know it's EI divided by 2. Again, it's already defined. We're good to go. Multiplied by the second derivative of our displacement function, so d. This d function right here takes a derivative, and it takes two arguments. The first is going to be, what is the function? So I'll say y. Ooh, we have a problem. I set you guys up. You all trusted me, and now I'm saying we have a problem. We don't have a single displacement function. We have two of them. We have YL and YR. So question for you all in the chat. Which one do I use? YL or YR? Ah, I'm separating you. It doesn't matter. So basically you could do this all as one integral, but the easier way to think of it is just doing it as two integrals. So I'm going to start off with YL, and this right here will be my strain energy on the left side of the beam. So we know it's going to be the derivative of our displacement function for the left side. We are taking it with respect to x1, and we are doing the derivative twice. So this would be the second derivative of my left displacement function. Now this is going to lead to the number one mistake. If I were to give you this assignment to do without my help, I guarantee a lot of students would forget this. So I want to make this clear, so hopefully you don't forget for the final. This second derivative function here, it's squared. So always remember that this function here is squared. The reason why a lot of students forget it, so I'm just going to put in the squared sign, is because for virtual work, it's not squared. It's only in the Rayleigh-Ritz method that it is squared. So this is going to be my strain energy on the left. If I wanted to, I'm going to copy the exact same function for the right-hand side. Strain energy on the right, and all I have to do is replace my displacement function from the left one to the right one. Now, question for you guys, is this good to go? Are you looking at this and saying, you know what, Clayton, great job. We accounted for the fact that we have two different, I couldn't even finish my sentence. You know exactly what's going on. The last thing we need to account for if we have two different displacement functions is going to be our limits. I can't integrate my left-hand displacement function for the entirety of the beam. If we look at our picture, it only goes from x1 is equal to 0 to x1 is equal to d. So what I need to do here is instead of going from 0 to L, I'm actually going from 0 to d. And on the other side, for my second displacement function, we know it starts at x1 is d and goes all the way until x1 is equal to L. So we're going to switch this one right here with D, and this one stays L. Are we good to go now? What do you think? Is everybody happy? It's really hard making all the students happy, so I'm hoping so. Happy? Perfect. So if we have a strain energy on the left and the right, could I find the total strain energy as the left one plus the right one? What do you think? Question mark? Is that good to go? Could I do that? Yeah, we can do that. Sorry for the delay. I got a private message. Is there a way to combine the left and the right displacement function into a piecewise function? You could, but I personally find this to be the simpler way. Otherwise, it gets a little bit gross. So I'm just going to leave that there. Now, question for everyone in the chat. Should this strain energy be a number or should it be a function? Basically, will I have an x1 term in my strain energy? What do you think? I'll go down here and we'll find out right away. What do you think while I'm typing this? Nah, exactly. So I'm going to put strain energy and I'm just going to go S. As we can see, it's simply just a number. We have 132, 651. Let's see if we got it right. I did what you all did and just put in a bunch of zeros. And if we look, it's very tiny on the screen, but we have 132, 651. So we're good to go. So we have our strain energy. So now at this point, if we were to go back to the assignment, we've completed part A, we've completed part B, and part C. The last thing that we are going to do is basically complete the actual meat of the assignment, which was find an approximate displacement function for the entire beam using the Rayleigh-Ritz method for a second, fourth, and sixth degree polynomial. As we're going to see, it's going to be quite simple. So we have our exact solution, good to go. We have our strain energy, good to go. And I'm going to come down here. And I'm going to have my approximate displacement function. So the first thing that we do, whether it's Rayleigh-Ritz method or the virtual work method, is we need to actually define what our approximation function is. The nice thing is the assignment told us we want three different cases: quadratic, basically fourth order, and sixth order. So we're going to start off with the simple one, but it's not going to last very long, as you'll see, and that is quadratic. So a second order polynomial. We know it's going to be a0 plus a1 times x1 plus a2 times x1 squared. So again, the first thing in the assignment asked us is it wanted a quadratic function. a0, a1 times x1 plus a2 times x1 squared. Question for everybody. What is the next step in the Rayleigh-Ritz method? I'll give you a hint. It's the same as the virtual work method. So what is going to be our next step? Can we go right into the idea of potential energy, or is there something we need to do to our approximation function first? What do you think? Exactly. Essential boundary conditions. In its current state here, we don't know if this approximation function satisfies all of the essential boundary conditions. So I'm going to go essential boundary conditions, and now I'm going to quiz you all. How many essential boundary conditions for this beam do we have? Keep in mind, I'm saying essential boundary conditions. All right, Aaron says 4. Anyone want to believe Aaron? All right, you agree with Aaron? I agree with Aaron too. Aaron was in my Eng 130 class, smartest kid I know. You can always agree with Aaron. So we're going to have boundary condition 1 is equal to, and if we look here, essential boundary conditions are always related to displacement as well as rotation. As we can see on both sides of the beam, we know that the displacement and the rotation must be equal to 0. So I'm going to say my boundary condition 1 is my approximation function when x1 approaches 0. So this is going to be the displacement on the left-hand side. I'm going to copy this and paste it. And I'm going to say this is boundary condition 2, which is my approximate function when x1 is equal to L. So this would be my displacement on the right. Now I'm going to incorporate boundary condition 3, which is the derivative of my approximation function with respect to x1 when x1 is 0. So this would be my rotation on the left. And then I'm going to copy it, paste it again, boundary condition 4, which again will be the derivative of my approximation function, but this time when x1 approaches L. So these would be my 2 displacement and my 2 rotations. Question for everyone in the chat: if I have 4 equations, how many unknowns can I solve for? 4 equations, how many unknowns can I solve for? 4. How many unknown coefficients do I have? What do you think? How many coefficients do I have? Am I trying to solve for? 3. So let's just take a shot in the dark here. Can I solve my approximation function just using these essential boundary conditions? Can I solve my approximation function for a second order polynomial using just essential boundary conditions? The answer is yes. So I'm going to use the solve function. So it's not dsolve, it's just solve because we don't have a differential equation. And it takes in 2 arguments. The first one is what are our equations? And the second one is what are the unknowns? So I'm going to put squiggle brackets because we have multiple equations. Boundary condition 1, which is the displacement. We know it's 0. Boundary condition 2, which is the displacement at L. Well, we know that's equal to 0. Boundary condition 3, we know that that's also equal to 0. This is the rotation. So I only need 3 because I only have 3 unknowns: A0, A1, and A2. What do you think those 3 are going to be? If you guys were to take a shot in the dark here, what do you think those 3 coefficients are going to be? 0, exactly. So if we were to solve it, A0 is 0, A1 is 0, and A2 is 0. So what I'm going to do is I'm just going to store them really quick. Is equal to A0, A1, 2, when solution 2, 1. So I'm going to store them, and then I'm going to put my approximate function. What is my approximation function going to be? 0. 0. Can you guys believe that? Isn't that crazy? And the reason why is this. I'm going to zoom in a bit here. If we were to look at this beam, and we are using a quadratic function, we know that the quadratic function is going to have kind of a smiley face here, right? If we were to use a quadratic function, could the slope be 0 at the fixed ends? Can the slope be equal to 0 at the fixed ends using a quadratic function? No, exactly. So that's why a quadratic function doesn't really work. So as we can see here, if we were to use a second degree polynomial, and we want in terms of a times b and then plus c, and I had it as 0 just to check the answer, if we were to scroll down, we got the correct answer. Isn't that nice when you're just guessing things and you somehow get it right? But as we can see, for a 4th degree or a 6th degree, we're a little bit off. So we need to go fix it. So what we're going to do is say, okay, quadratic, we know it's going to be 0. But let's go to our function and let's look at the 4th order. So I'm going to say plus a3 times x1 to the exponent 3 plus a4 times x1 to the exponent 4. So now we have our quadratic function, or sorry, our 4th order function. We have 4 boundary conditions, so I can actually add in all of them now. So BC4 is equal to 0, which allows me to solve for one more variable, a3. And then we can store them. So we're going to have a3 here, and we are going to have a3 here. So I'm going to actually delete this really quick, and I'm going to unsuppress this. We're going to run it. And as we can see, by incorporating the essential boundary conditions, we know that a0 is 0, we know that a1 is 0, and a2 as well as a3 can be a function of a4. So notice that a2 and a3 don't actually go to 0, but they can be rewritten as a function of a4, which is nice because if we were to look at our approximation function, a0 is 0, a1 is 0, a2 is a function of a4, a3 is a function of a4, and then we have a4. So what will actually happen, I'll just create some room, if we were to call our approximation function, as we can see, our only unknown coefficient is going to be a4. That's it. So this is when we actually have to start using the Rayleigh-Ritz method to solve for that final coefficient, a4. So we do that by basically minimizing the potential energy of the system. And we know that the potential energy basically has 2 components. The first one is the total strain energy. And we've actually already did this above. We know that the total strain energy is the integral over the length of the beam of EI divided by 2 multiplied by the second derivative of our displacement squared. So what I can do here is I can say, okay, my total strain energy is going to be an integral, so I'm going to use the integrate function. We know it has 2 arguments, just like above. And the second argument is what is our bounds. So we're going to go from x1 is 0 to L. Question for everyone in the chat, because you all said that above here we had to change our limits, as you remember. Do we have to change our limits for this total strain energy? No, exactly. That's the beautiful thing about the Rayleigh-Ritz method, is for this beam, even though we know there's going to be a discontinuity, basically the Rayleigh-Ritz method doesn't care. We can still approximate this whole beam using one function. So this will stay the same as over the length of the beam, and we know it's going to be EI divided by 2 multiplied by the second derivative of our displacement function squared. So I'm going to add in the square, and I'm going to have my derivative function. We know that we are taking the derivative with respect to x1 and doing it twice, and then here we need our displacement function. What is our displacement function? Do we know what it is? Do we know what our displacement function is? Yes, it's going to be y approx. So that's one thing that I actually got a comment on one of my finite element videos, is they said, Clayton, we can't use any of these equations because we don't know the exact solution. You're right, we don't. But we do know an approximate solution. So this is what we would throw in here. Now, question for everyone in the chat. Would you expect this total strain energy to be a function of x1? Will this be a function of x1? No. We're integrating with respect to x1, so if I were to go to the total strain energy, as we can see, it's just this big, long, complicated mess right here. So I'm going to suppress this, I'm going to suppress this, and say, okay, we did total strain energy. Now we need the work done on the system. And we said, well, this is actually pretty simple. If I were to go to the lecture notes, we know that the work done on the system is going to be the integral of the distributed load. Well, we have none, so that's 0. Plus the summation of any moment times its rotation. Oh, we have none either. And then plus the summation of any point loads times its displacement. Well, we do have one point load. So I'm going to go back here and say, okay, my work is going to be my point load P times my displacement. So we said that our displacement, oops, is y approx. So question for everyone, is this correct? Is this correct? We have P, we multiplied it by displacement, which is what my equation told me to do. Am I good to go? Ah, yes. So Gabriel's correct. When we're dealing with the displacement at a point, we have to substitute in that point. Again, here's going to be the trick. Both your total strain energy and your work done on the system should not ever be a function of x1. If I were to just run it, as we can see, it's a function of x1, which is a problem. If we were to look at a distributed load, we multiply by the complete displacement function, but then we integrate from 0 to L, which gets rid of the x1. Since we don't integrate, we actually have to specify that this point load acts at a certain location. So we know that it's going to be P times our approximation function, specifically when x1 is equal to D. Again, we're saying that this point load P acts at x1 is equal to D. So good call, you guys got it. And if we know the total strain energy and we know the work done on the system, we can find the potential energy of the system. Because we know that the potential energy is the total strain energy minus the work done on the system. And that's it. I'm not going to express it, I'm going to run it. And as we can see, we have an equation. And our only unknown is going to be A4. So let's see who remembers. How can I figure out what A4 is equal to? What do we do with this potential energy to solve for A4? Differentiate, exactly. We know that we want the potential energy of our system to be minimal. That would result in a stable equilibrium. So we're going to create a section, minimize the potential energy. And what I'm going to do is I'm going to create an equation. And this equation is going to be the derivative of my potential energy with respect to whatever unknown A coefficients we have. So if we remember, our potential energy right now is just a function of A4. That's it. So we're going to take the derivative with respect to A4. From here, we're going to solve our system. Because we know that we want the potential energy, equation 1, which is the derivative of the potential energy, to be minimal. In order for that to be achieved, we know equation 1 has to be equal to 0. And if we have one equation, we can solve for one unknown. In this case, we're going to solve for A4. So if I were to run it, as we can see, we now have a value of A4. Isn't that fantastic? So what I'm going to do is I'm going to just store it. Actually, I'll put a solution 3. And I'm just going to store A4. Perfect. And then now, if I were to go my approximation function and I were to call it, is there going to be any unknowns? What does everyone think? Will there be any unknowns? Am I good to go, basically? Yeah, Aaron raised a good question. If you're just doing one, you don't need the squiggle brackets. I just put them in because we are going to do the 6th order right after, and we'll have A4, A5, A6. So I'm just saving myself some time later on. Good question, though. Well, let's just run our code and see what happens. As we can see, we now have our equation, and it's actually good to go. So what I'm going to do is I'm going to put it in my display the results section. So print approximate solution. I'm going to go y_approx, and I'm just going to put expand for good measure. And as we can see, we now have our approximate solution. Question for everybody in the chat. Do you think that this approximate solution is pretty good? Remember that our exact solution had x to the 3, and that was it. And in here we have x to the 4. You think it's pretty good? All right, you all think it's good? Well, let's see. So I'm going to take this piece of code from our virtual work code from before, and this is basically just going to plot everything. So one thing I'm going to do really quick is I'm just going to calculate the shear in the moment. Basically get all these variables. So I defined it as m_approx and v_approx. I guess EI times the derivative of y_approx x1, comma 2 for moment. For shear, it's going to be the exact same thing except the third derivative. So this will be 3. This will be v_approx. And then I have YL, YR, good to go, but ML and MR, which will be right here. Time to get your bets in if you think that this will be a good approximation. You all seem pretty confident, so I'm having faith in you. Isn't coding fun? Just a lot of copy paste. All right, that looks good. Usually you find the errors after you run the code. So let's see what we got. So here's our 3 plots. We have deflection, we have moment, and we have shear. Is that a good approximation? Gabriel says it's good enough. Was it good enough? It depends. But Aaron says no. And it's one of those things that we don't know. It depends on what we're doing. So Gabriel's correct. But here's the thing. And this is the hard part about the finite element method, which everyone starts to get confused. We use the finite element method because we don't know what the exact solution is. We don't know. So if I didn't plot this with the exact solution, let's say I just plotted the approximate solution, would you be able to tell if it was a good approximation or not? If we didn't know the exact solution, could we tell if this was a good approximation? No. That's the scary part about the finite element method. What the finite element method relies upon is this. If I were to start increasing terms, adding more and more terms to my approximation, what you'll see is that the approximation will almost become constant. If I were to go to the 6th order right now, I would expect basically a drastic shift in the approximation. But if I were to go to the 8th order, I'm expecting that it would actually look very similar to the 6th order. So that's how you tell if you're actually approaching the correct solution. It's called convergence, where basically by adding more terms, your approximation function almost starts to look the same no matter how many you add. So we said that this is not a good approximation. But what happens if we do the 6th order? So remember, the assignment also says it wants the 6th order. So we're going to go plus a5 times x1 to the exponent 5 plus a6 times x1 to the exponent 6. Here's the nice thing, is once you have the basic code down, it's very easy to change our approximation function. So all I did was I added in our additional 2 terms. Will our essential boundary conditions change? What do you think? Do I just leave this piece of code? Exactly. So nope, this does not change. This code stays the same. My total strain energy. Do I need to change this piece of code? Do I need to change my total strain energy? No, exactly. How about the work done on the system? The answer is nope. Potential energy? Nope, because it's a function of the strain energy and the work, which don't change. Well, minimizing the potential energy change. Well, this code needs some modification. Yes, and again, the reason why is because here we're solving for our unknown A coefficients. At this point now, we'll actually have A5 and A6 as unknowns as well. But it's very simple to accommodate them. All I would have to do is create equations for each one. So we'll call this equation 2. We'll call this equation 3. And instead of differentiating with respect to A4, we are going to do it to A5 and to A6. From here in my solve function, I'm just going to add my additional equations. Equation 2 is equal to 0. Equation 3 is equal to 0. And add my extra unknowns. So A5 and A6. And this is why I put the brackets down here initially, because now I can just add A5, A6, A5, A6. Am I good to go now? Is my code good to go now? John says nah. What does everyone think? Well, the best way to check is just to run it. So if I were to run it, oh, it's good. Now, is this a good approximation? Yes, exactly. It's a good approximation. Solution 1, I had it as solution 3. Because we had solution 2 above and we had solution 1 even more above. So this is the last thing I want to leave you on when it comes to these approximation methods. Because this is what happens a lot that you'll see in the finite element method. Deflection, really good. Moment, it's pretty good. Shear, remember there's a kind of a bar way up top here, and then the discontinuity, and then constant. Shear is kind of iffy. So what you'll find out for approximation methods is that adding more terms will get you a really good actual approximate solution. But then down here, the more times we take the derivatives, that's when it really starts to show that it is an approximation. Again, as we can see for the shear, it gets really weird. And the problem is we are trying to model a discontinuous function, basically we're trying to model a discontinuous function using a continuous function. So for essential boundary conditions, do we always want the most we can get? Yes, absolutely. Absolutely. Because what would happen if I were to not include one of them, I wouldn't have, let's say, the displacement at this end is equal to 0 or something like that. So that would be very important. You definitely want to include every single one. So yeah, that's going to be the assignment. So if we were to look back at the assignment now, it wanted the exact displacement, we did, for both of them. It wanted the strain energy stored, we did that. It wanted the approximation for a second, fourth, and sixth degree polynomial, we did all three. The only thing that you will have to do is just comment on the accuracy, and we basically also did that together. So this is the code, and actually no, this is not the code. No, this is the code. And this will be posted to eClass. So that is assignment 10, which is your last assignment, if you don't count the bonus assignment. But for the bonus assignment, again, you can do the abacus. I'd be happy to see it. But the easier way would to just take some time for yourselves. That would make me more happy. I would love to see everyone play around with the finite element method because that's what I teach. But I would love it even more to know that you all took a break and had some fun. So remember, assignment 11, most of you have already responded, but if you haven't, just take some time for yourself. That's all I want. Assignment 10, done. So I can say with pretty confident certainty, you're done for this course besides the final. So congratulations, everyone. It's been a good semester, and I'm very happy with how it turned out. So thank you all for making it so amazing. Is there any questions before we end today's lecture? All right, if you're okay, I got a direct message. I would have to see the code, so I won't mention your name, but just send me the code and I'll let you know. Now I'm getting some nice private messages. Thank you guys, I really appreciate it. I tried to make the course as fun as possible. I know that I can speak from experience by saying that this course is not really super interesting. If you don't like simulation, then this is probably one of the worst classes you can get in civil. But I personally love it, so hopefully I can spread my joy with you guys. No problem, everyone. I will see you Thursday for the finite element method, but always remember that that stuff will not be tested on the exam. This is the end right here. So